Let me go to the screen, share the screen with you, and here you go, and you can see. All right, hide. All right, so basically this is the slide we had last time. Is it right or wrong? Is it right? Everybody okay? Yes, this is the slide that we had. So that's basically gives us the definition of buffers, right? And the equation that we routinely use for the buffer is pH, right? pH equals pKa, K is the dissociation constant of an acid, plus log of concentration of A minus, just a minute, concentration of A minus, that's a conjugate base, divided by concentration of undissociated acid. That's the Henderson-Hathaway equation. Does anyone have any question on this equation? This is the equation used routinely.
I have a question. So it's pH equals pKa plus the log of like that stuff. What does the P represent in like the pKa?
pKa is a negative log of Ka, and pH is routinely used, and pH equal negative log of concentration of hydronium ion. Those are routinely, those are by definition. Yes. Any other questions? If not, let's go to some. Let's solve some problems.
Like an example of this.
Yeah, I will give you. Just wait. Now, let's go to question number 1. Question number 1. Let's solve it for me, and I'm waiting. Acetic acid has Ka 1.8 times 10 to the minus 5, and phosphoric acid has Ka 7.8 times 10 to the minus 4. Which one is the weaker acid? Which one is the weaker acid? So please try to understand. So Ka value is used to determine the strength of weak acids. And weak acid could be 95% dissociation, 0.1% dissociation. How do you justify? By using by knowing their Ka values. And Ka values could be determined by experimentally. All right. So by looking at the pH, in fact. So if the acetic acid has Ka 1.8 times 10 to the minus 5, and phosphoric acid has Ka 7.8 times 10 to the minus 4, which one is the weaker acid? Come on, tell me. Yes. So how do you do that? Tell me, how do you do that? So answer question number 1. Answer to question number 1 is, this is the way it goes. So higher the Ka values, stronger the weak acid. Higher, this is the rule, huh? Higher the Ka values, higher the Ka value, right? Stronger the weak acid. Remember, we are talking about we are differentiating within this weak acid. So stronger the acid. So remember this. Now tell me, question about what is the answer? I just give the statement. Higher the Ka values, higher the Ka, stronger.
7.8 times 10 to the negative 4.
Yeah, meaning phosphoric acid, right? Does it mean?
Yes.
Yes. So phosphoric acid is a stronger acid among these two acids that we compared. And this kind of question you can see in the test, of course. So higher the Ka, stronger the acid. Lower the Ka, weaker the acid. So now wait a minute. So stronger. So which one is stronger acid among these two? The question is, which one is the weaker acid? Which one is the weaker acid? Higher the Ka, stronger the acid. Acetic acid. That is correct. Because acetic acid has 10 to the minus 5, and this one has 10 to the minus 4. 10 to the minus 4 is less than 10 to the minus 5, 10 to the power minus 5. We are looking at only that one is less than 10 to the power minus 4. Yes or no? Therefore, acetic acid is the weaker acid. Phosphoric acid is a stronger acid. Everybody okay? Any questions?
I have a quick
Next.
question.
Yeah.
So for that type of question, we don't need to calculate anything, right? We just look at the variables and figure it out from there.
Just look at the number.
Okay.
That is, just look at the number. Very simple question. Very simple question, but you will be able to do it, no problem. But knowing that higher the Ka, stronger the acid, lower the Ka, weaker the acid. We are comparing within weak acid, okay? We are not going to the acetic phosphorus, the HCl, nitric acid, sulfuric, those strong acid. We are not talking about those. Within the weak acid, they could be differentiated whether how weak is weak based on the Ka values. Ka values. Now, who can calculate the pKa for the acetic acid? I think someone already did. We're going to make another general statement. So pKa of acetic acid. Can someone give me? You gave me before pKa of acetic acid. pKa of acetic acid. So what's the
When you
pKa?
take
Huh?
the negative log of Ka.
That is correct. So negative log of this value. The pKa of acetic acid is negative. That's right. Negative log of, put the all those things, 1.8 times 10 to the power minus 5. That is correct. Yes. Give me the value. Give me the value.
4.73.
Huh? 4.
4.73.
Yeah, good enough. Good enough. Excellent. Everybody okay with it, right? Remember, this type of question will be there in the test. Now, pKa of phosphoric acid. Tell me, pKa of phosphoric acid. It should say pK1. Phosphoric acid has 3 of them, but that's okay. It's a pK1 because it has 3 protons. It will dissociate 3 times. pK1 equals, who can tell me? Same way. Negative 2, let me write down. Yes, then I'm going to put your number. Times 10 to the power minus 4. And you said, what's the number you said? 3.11. 3.11. That's fine. That's fine. 3.11. I can change the number if when I ask the question, but if you should know how to do that. 3.11. That is perfectly fine. That is perfectly fine. Very good. So now, what type of relationship can you derive from the Ka values and the pK values? So higher the Ka, stronger the acid. How about in terms of pKa? In terms
Is
of
it that?
pKa,
Is
Huh?
it the higher the pKa, the weaker the acid?
that is correct. That is absolutely right. As you can see from here, higher the pKa, weaker the acid. It's an inverse, exactly the inverse, opposite. And why is opposite? It's a negative log. It's a negative log of the number, negative. That means we're talking about the opposite sense. That is correct. This is just a general statement. I'm not writing it, I'm telling you because you already told me the answer. Higher the pKa, weaker the acid. Higher the pKa, remember this type of question will be there, entertained, right? Higher the pKa, pKa, not Ka, huh? Higher the pKa, that give you weaker the acid. That is correct. Weaker the acid. Please remember this. This is very important because some of them will be tested, and you should know that because these are very good applications. Okay. All right. So that's basic. So higher the Ka, stronger the acid. Lower the Ka, weaker the acid. Higher the pKa, weaker the acid. Lower the pKa, stronger the acid. All right. Everyone okay? All right. Let's do the question number 2. Give me the answer for the question number. Yes.
Do you have to have units after the numbers?
No units there.
Okay.
They're unitless. Yeah. Yep. Very good. Now, next one, question number 2. Please do the question number 2. Who can do the question number 2 for me? I used a lot of space here, but let me see whether I can put a line here and do the rest of it. Solution contains 0.5 molar acetic acid. Acetic acid. So that's your HA. Remember, okay? Acetic acid is already spelled out. And 0.25 molar sodium acetate. Sodium acetate. Remember, acetic acid gives the acetate ion. So that's your A minus. The sodium salt of this is A minus. So HA is acetic acid. A minus is 0.25. What is the pKa of the solution? Come on. pH. Remember the Henderson-Hasseby equation, right? That's why you determine the Henderson-Hasseby equation. pH equal. What shall I put? The next one. What shall I put? Come on. You already did that. You already did the calculation.
pKa, which is it, which would it be 4.73?
Why not? You can say the confidence. Yes. pH equal 4.73 pKa plus log of what shall I write? What shall I write?
Is it it's the log of A minus divided by HA?
That's the Henderson-Hasseby equation for the buffer. That is correct. So what shall I write? pH equal 4.73 plus
The log of 0.25 divided by 0.5.
That is correct. Very good. And give me the number. Give me the number. Oops, sorry. Give me the number.
4.43.
Yeah, sounds good. 4.43, that's what you say, right? Yeah. Yeah, that is correct. So 0.25 divided by 0.5 is 0.2, I guess. Yes, 0.2. And log of 0.2 is minus 3.30. Yeah, that is correct. So subtract that from this and this. This will be in the test. I mean, not this kind of exactly the same one. I can ask phosphoric acid, I can have formic acid, but I will give you the pKa. Ka. You have to calculate the pKa, and then you can plug it in. And always remember, the acetic acid concentration, the acid concentration will be given to you definitely. Once you find the HA, whatever the other number is the A minus. So just plug it in. First calculate the pKa. Ka value will be given to you, and then you just plug into the equation, and you get the number. All right, 5 points, 4 to 5 points minimum. Okay. All right, I'm going to move on. Any question for this? How to calculate the pH? How to calculate the pKa? Sorry. Huh?
So for the log, is the 0.25?
So what you need to do? 0.25 divided by 0.5 first. Get the number and hit the log.
Okay, got it.
Yes, absolutely. Any other questions?
How do you know? Sorry.
One at a time, please. Go ahead.
How do you know, like, which one's the A value and which one's the HA value?
So if the name says the point, let's say if I say 0.3 molar phosphoric acid, you know the phosphoric acid is weak acid, right? Yeah. Therefore, that's a HA. We define the HA as a weak acid, right? So that will be given, so 0.25 phosphoric acid. So that's the HA. And then the next number will be given 0.15 sodium phosphate. It's usually the salt. A minus is always salt. A minus cannot exist as it is, right? It has to be counter on sodium phosphate or potassium phosphate or something like that. So that's A minus. That's how you can define. That's how you can identify which one is which. Is it okay?
Yeah.
All right.
Thank you.
You're welcome. All right, we're going to the next step. Is it okay? Anyone has a question? This type of question will be there in the test anyway, without any question. Okay.
I
So does
have
the
a,
weaker acid go on the bottom?
Huh? Say it again.
Does the weaker acid go on the bottom?
Yep.
And the stronger acid on the top?
That's the Henderson-Hatchell equation is pH equal pK plus log of concentration of A minus conjugate base divided by concentration of weak acid. That's the equation you have to remember. Is it okay?
Why is
All
it
right.
0.25
Yeah.
divided by 5?
And say it again.
Why is it 0.25 divided by 0.5?
Because A minus, concentration of A minus divided by concentration of HA. Do you have the Henderson-Hatchell equation with you? Right here. Log of concentration of A minus divided by concentration of HA. Okay? All right. Let's move on. All right.
I have a question real quick.
Yeah.
How, like, if I was taking a test, how do I know which is A minus and which is HA? Like, how do I determine that?
I just said it. So it will be written like this: a solution contains 0.35 molar phosphoric acid. So I'm saying it, phosphoric acid is acid, HA. Then there will be another number next to it, that is the A minus. And A minus is always a metal salt, is a salt, like a magnesium acetate, sodium acetate, potassium phosphate, sodium phosphate. Those are salt. So that's your A minus. A minus. A minus is always salt. Yeah. Any other questions? If not, let's go to the next one. Applications of the buffers. And those are the most important one, juicy one, right? We must know buffers in our body, human body. In buffer, we have a 3 buffer system in our body. One is called open system, that has a bicarbonate H2O3 minus and carbon dioxide dissolved. And this open system, because it is open to the environment, and that's a physiological condition, because as all you are breathing, I'm breathing, everybody is breathing, and that's basically the carbon dioxide from outside. Carbon dioxide from outside is maintaining the pH of our blood, and if it is stopped, everything gone, right? So that's basically, and that's a physiological condition. So open system, it is in our circulatory system, the blood system, and that has a minus. This is our A minus. This is our A minus, and CO2 dissolved doesn't look like it's acid, but that's actually like an acid. Now, I'm not going to derive this equation. It's a long equation. You don't have to derive for this class at least, right? We don't have to derive, but this is A minus. That's HA. So conjugate acid and conjugate base. What basically happens is as follows. You remember the carbon dioxide gas as you breathe in. So carbon dioxide gas, it goes inside our lungs, right? And it becomes carbon dioxide dissolved. Carbon dioxide dissolved. Carbon dioxide goes inside the lungs, and carbon dioxide dissolves. Basically, that's a D stands for dissolve. This stands for dissolve. And then this one react with the H2O, water in the blood serum, and that's makes carbonic acid, H2CO3. H2CO3 further reacts with the water, is acid, right? It dissociates with the water, and that generates hydronium ion, H3O positive. Please write down this important one, right? Plus HCO3 minus. So now think about it, how it coming there. Carbon dioxide gas from outside. Carbon dioxide comes from 2 sources. From our breathing in and out. Another comes from the metabolic processes. When you eat, it goes inside the cell. Then ultimately it goes to glycolysis. We'll talk about. After the glycolysis, it goes to the TCA cycle. In the TCA cycle, it generates plenty of carbon dioxide. Plenty of carbon dioxide. That happens to mitochondria. That carbon dioxide dump into the bloodstream again. So carbon dioxide comes from 2 sources, breathing in and out, and another one coming from the metabolic processes. That carbon dioxide gas, once it goes to the lungs, lining the alveoli cells, probably some of you know, right? and that basically it is dissolved, it is absorbed inside. And the enzyme, there is some enzyme there, but we'll not talk about more, maybe down the road. And then once it gets inside the blood cell, blood has a serum, water that reacts, make the carbonic acid. Carbonic acid further dissociate into hydronium ion plus HCO3. So if you take those account all of this, and that's become after derivation, I'm not going to show you the derivation, it's a long derivation, you don't need it. And then it comes like the A minus is HCO3, that's HCO3, and carbon dioxide dissolved right here, that acts like an acid. It is in equilibrium with the carbonic acid anyway. So instead of carbonic acid, carbon dioxide dissolved is the one HA. And carbon dioxide dissolved in equilibrium with the carbon dioxide gas, outside or inside. That's why it is called open to the environment or physiological response. So you can derive the Henderson-Hasselbalch equation for this dissociation, because you already know A minus and HA. pH equal, that's the pK you have to remember, because it came from all those things. I'm not going to derive the equation again, it's a long derivation. pK is 6.1 plus log of concentration of carbonate, bicarbonate, divided by concentration of carbon dioxide. All right. Now, is it a good buffer or not good buffer? Excellent buffer or not buffer? Someone asked the people, how do you define an excellent buffer, a good buffer? Does anyone know? A buffer is an excellent buffer when the required pH is close to the pKa. Please write down. An excellent buffer is defined as a buffer or a mixture of solution, right? A solution that has the solution containing weak acid and a conjugate base that has pKa is very close to the required pH, very close to the required pH. Who can tell me what's our physiological pH? Can anyone tell me what's the physiological pH? What is our body pH? Does anyone know?
Is it 7.4?
Absolutely right. You know that very good. It's 7.35 to 7.45 is the range. Average is 7.4. So our required pH of the blood or inside the cell always 7.4. And pKa after all those things, dissociation, is 6.1. It's not too bad. It's pretty close. It's pretty close, but it depends upon the concentration of carbon dioxide. And bicarbonate concentration inside our blood is fixed. It's about 24 millimolar. 24 millimolar. We can write down 24 millimolar. And carbon dioxide dissolved, it varies, and that is 1.2 millimolar. So 1.2 millimolar carbon dioxide, and that is variation. Because it's equilibrium with the carbon dioxide, also equilibrium with the carbonic acid. So bicarbonate concentration inside our blood, almost everybody, all the red-blooded animal, red-blooded creatures, red-blooded living species, they were 24 millimolar bicarbonate, and carbon dioxide dissolved is 1.2 millimolar. All right. So if you do the calculation, log of 24 divided by 1.2 is a 0.3. Add it up, 6.1 plus 0.3, 1.3, not 0.3, 1.3, and add it up. 6.1 plus 1.3 is 7.4. 7.4. So that's basically our maintain the pH. Everybody okay? Any questions? All right. If not, now since this equation depends upon the concentration of carbon dioxide dissolved, and that can vary, and therefore it has two different conditions called pathological conditions. These are very bad, by the way. One such, if the concentration of carbon dioxide inside the blood is too much, concentration of carbon dioxide is too much, then what will happen? If the concentration of carbon dioxide is too much, what will happen to the pH? Can someone tell me? If the concentration of carbon dioxide is too much, look at the equation. pH equals 6.1 plus log of concentration of bicarbonate divided by concentration of carbon dioxide dissolved. If the concentration of carbon dioxide is high, very high, what will happen to the pH?
Would it
What
go
will-
up?
It will go down. Because go down is a denominator. It will go down. It will go down. So too much carbon dioxide in the blood, meaning acidosis. That disease is called acidosis. Too much acidic, too much carbon dioxide. Carbon dioxide is equal to the acid, right? If you have too much acid in the blood, that leads to the acidosis. And the disease associated with acidosis are COPD, asthma, all those related to the lungs, lung disease. What is the COPD, by the way? What is the COPD? Anyone? Chronic obstruction of pulmonary disease. Chronic obstruction of pulmonary disease. Does anyone have seen any patient with any person with asthma? Have you seen any asthma patient? Does anyone?
Yeah.
No offense. No offense. Yeah.
Yeah.
Yeah. Some people get exercise induced too. And what do? They breathe. They have a breathing trouble. They have a breathing trouble. What basically happened?
Me out and Cole were sitting in the living room.
Someone turn off the microphone, please.
I looked
Yeah.
at the wall and I was like, "What is
Yeah.
that?"
Someone turn on the
There's
microphone.
literally a freaking slug on the wall.
Hello.
Madison, turn off your
And
microphone.
so I was
Turn
like,
off the
I'm not-
microphone, please.
Cole, you're
Thank you.
Madison, your mic's
I
on.
was going ask the neighbors to get it because there's a thousand
Hello?
slugs across the wall. So Cole got like I was holding a dick.
Turn off the microphone, please.
Outside.
Hello.
And as soon as
Turn off the
Cole wanted
microphone,
to-
please.
I like screamed.
Hello. Turn off the microphone, please. Don't let me sound. I don't want to, right? Yeah. All right. So the pathology. So too much carbon dioxide causes the acidosis, and that the disease associated with those is chronic obstruction of pulmonary disease or asthma. What basically happened? Those patients or those people, their windpipe collapses. The windpipe is the one exchanging carbon dioxide in and out. Since it collapses, there is no carbon dioxide coming out from the body, from the blood, and metabolic system is on, making plenty of carbon dioxide, dumping into the blood, so carbon dioxide content going up and up and up and up. And that's why the pH is getting lower and lower and lower. If the pH goes 1 unit lower, 0.1 unit, 7.3, we are in big trouble. And that's basically happened because during the acidosis or COPD, asthma disease. Some cases is genetic, some cases is, but it's not an end of it. As you know that many people take the inhaler, right? Inhaler, you can take the inhaler and perfectly fine once you spray it, and windpipe opens and everything is fine. But it has to be done within 15 minutes, 15 to 20 minutes. If this COPD or asthma continues for 15 to 20 minutes, the patient will die without any problem. Because what happened? Too much carbon dioxide make too much acid, carbonic acid. That carbonic acid will denature all those blood proteins, hemoglobin, some other serum proteins, etc., etc. Hemoglobin is denatured, no oxygen binds, person suffocates and dies. So very dangerous disease. But as I said, it's not inhalers are there. Some cases, some medicines are also there too, to get to make the strong the lungs stronger, and windpipe also heals up by some disease from medicines as well. Now, if the opposite case happen, if the carbon dioxide gas is too low in the blood, carbon dioxide gas is too low in the blood, that leads to the higher pH. In principle, if the carbon dioxide is low, right, the pH will increase, and within 15 to 20 seconds, that goes to 7.74, just a very fraction of a second or a few seconds, and then all those proteins and everything will denature and everything will be gone if it persists. So the lifespan again 15 to 20 minutes. The pH goes 7.74 within 15 to 20 minutes, and that leads to the disease called alkalosis. And CNS disorder like meningitis, encephalitis, epilepsy, etc. All those diseases are associated with the alkalosis. Depression drugs, steroid drugs, anesthetics, they can all lead to the disease called alkalosis. What basically happened, and also people in a burning building or something like that, they basically breathe a lot, breathe heavily, high fever. If someone gets the high fever 105 or on something like that, towards that, and high temperature, carbon dioxide is a gas, it will come out, and they will basically breathe very heavily, sweat a lot, and therefore that leads to alkalosis. So remember these two conditions, okay? It will be in the test. Another buffer that we have is called closed system inside the cells, and that's coming from the these two, phosphoric acid. So this is our H and this is our A minus, HPO4 2 minus divided by H2PO4 minus, and that's our HA. So phosphoric acid has 3 protons, remember, right? It can dissociate 3 different times, and one of them, the middle one, usually the appropriate pH for our cells, and all those enzymatic functions depend upon the pH, and usually there's no disease associated with this because it's inside the cell. So inside the cell there's no problem with that, right? Therefore the Henderson-Hathaway equation looks like this: pH equals pK, that middle pK for the phosphoric acid is 7.2 plus log of concentration of HPO4 2 minus divided by concentration of H2PO4 minus. And our required pH is 7.4, right? 7.4, and you have a 7.2 pKa, very close, and therefore you don't need much. You need only 12.75, 12.75 millimolar concentration of this, and this is our 12.25, and this is 7.75, and that's good enough to maintain the pH inside the cells. There's no disease associated with this.
Can you
But
repeat the concentrations of the two?
Sure. This is a 12.25 millimolar. This one, this one, and this one is 7.75 millimolar. Yes, very good. So these, if we add them up, is a 20 millimolar, and it's constant. It's constant.
How
Shall I
do
move
you
on?
make it?
Shall I
Where do you
have?
get those numbers from?
I'm not going to give it to you. I know this, you can calculate this. So the way to calculate is as follows. You can calculate those. By the way, there's some mathematical. So since the pH is 7.4, right? The pH we record is 7.4. So you can do like this way: 7.4 minus 7.2 is 0.2 equals log of this. Then take the log of, in the other side will be 10 to the power 0.2, and that will give you 1.58, the ratio. And inside our cells, concentration of HPO4 2 minus and concentration of H2PO4 minus is 20 millimolar. And so you know the ratio of these two, you know the addition of these two. From this, you can calculate these two. I'm not going to show you, but definitely yes. Yeah, there are some procedure to do that. I'm not going to get to making it too complex for you. Is it all right? All right. Next, move on. Now, next one is the how do you see the pH? Do you need to have an indicator, or do you have to have a machine all the time? Will we carry the machine? Answer is no. There are some indicators are available to calculate the pH very routinely, very within a few seconds, within a few minutes at the most, minute or two. And indicators are usually large molecular compounds. These molecular compounds changes the color at different pH. You must remember what's the indicators. Indicators are large molecular compounds, changes the pH, changes the color at different pH. Example, probably many of you know, litmus paper. Red at pH less than 7 and blue at pH 7% greater than 7. So red and blue, you can always see that, right? And I gave you some list. You don't have to remember the list, but definitely you must remember some of those. As you can see, this is the pH range, and some of them from yellow to violet. For example, here, the thymol blue, for example, red at pH 1 to 2, and yellow at pH 3. So very short range, they can change the color. They can change the color. Based on this color change, you can say, what do we have these? These compounds are usually put in the paper, a piece of paper. And you take the piece of paper, dip into the solution, and then you can see the pH. And it is an excellent application. No offense, right? Excellent application is a pregnancy test for the woman. And as you probably know, blue, clear blue, I'm not giving any commercial to anybody. This is a company, it makes a strip, and that strip has all those things inside. So what you do, what the woman, if a woman wants to test whether pregnant or not, take a little bit sample, urine sample, usually urine pH changes during the pregnancy, and it will give the blue or red. And based on that, is a blue means the pregnant is yes. All right. So then it has the clear blue. It has a strips in there, and that is the indicator. And take some urine, dip it in there, and that's it. Within a few seconds, maybe a few minutes, and then you can see the color change. And that's why the quick test, quick pregnancy test by using the indicators, and that depends on the different pH. And women once they're pregnant, the the pH of the urine changes. pH of the urine changes. I'll give you some list of the urine, list of some of the pH of some common materials. You don't have to remember, but take a look at it. Battery acids in your car, 0.5, very is sulfuric acid in there. Gastric juice, 1.0 to 3.0. Pancreas dumping into the food, that's on the stomach. Lemon juice, 2.2 to 2.4. Vinegar, 2.4 to 3.4. Tomato juice, 4.4 to 4.4. Carbonated beverage, 4.40 to 5. Black coffee, those are all acidic, right? They're all acidic. Milk is acidic too, 6.3 to 6.6. Now, who can tell me why the milk is acidic? Can someone tell me the composition of milk? What does it have? Does anyone know? Milk has plenty of ...
Calcium.
Lactose.
Yeah, lactic acid. Yeah, right. Lactose. Yes, that's correct. Lactose. And if it is aged, it will be lactic acid, and the milk is gone, spoiled. Right? You dump into somewhere. You cannot drink that one. A poisoner. Saliva is varies depending on the person. 6 points. It could be acidic to alkalinity to acidic to basic. Pure water 7.0. We talked about it. Blood pH. Someone gave me in the morning. Is 7.35 to 7.35 to 7.45. 7.4 is the average. Bile acid. That's basically our gallbladder, right? Our pancreas dumping plenty of it for the digestion. 6.8 to 7.0. Pancreatic juice, pancreatic fluid, 7.8 to 8.0. That's all the enzymes are basically working. Seawater 8.0 to 9. Soap 8.0 to 10. That's why you see the bitterness, right? Once you go inside your mouth. Milk of magnesia, you neutralize the acidity, right? If you have acidic stomach, the 10.5 is ammonia has 11.7. Lie. You don't want to go there. 1.0 sodium hydroxide, 1.1 molar sodium hydroxide has pH 14. All right, so these are some common pH that you should know. You don't have to remember, but at least you should take a look at it and how there are many other things there too. All right. Now that gives us the practice homework assignment. Please write down. I'm going to wait for you, and you must solve it. These are the one who will be in the test, or not exactly those, but definitely there are many things will be in the test from there. It has the basic concept. All those basic concepts are in there. Applications are, we have discussed in the class, and so our test is coming next Monday, right? Next Monday on the following Monday. So what are the origins of acids? What are the origins of bases? What are conjugate acids and bases? How do we define a strong acid and weak acid? You already know, right? And then how do we define a stronger or weaker acid within the weak acids? That's the Ka values. We talked about it, right? Just talked about today. What is pH and pOH of a solution? There's a negative log of concentration of hydronium ion, negative log of hydroxide ion, and if I give you some concentration of acid concentration, you can determine the pH, and you can also determine the pOH. If you know the pH, 14 minus pH equal pOH, and vice versa. If you know the pOH of the base, then 14 minus pOH is the pH. If the pH of a solution is 9, what's the pH? You already know probably. You can say it from top of your head. Just example. What is the pOH of a solution containing 0.75 molar sulfuric acid? Did you see that? What is the pOH of a solution containing 0.75 molar sulfuric acid? Sulfuric acid is acid. So you must determine the pH. We did it in the class. If you look at your notes, they're all there. Then once you get the calculation of the pH, subtract from 14 to get the pOH. Likewise, what is the pH of a solution containing 0.5 molar barium hydroxide? Barium hydroxide is not acid. So therefore, we are not talking about a pH. So you should calculate the pOH. And once you get the pOH, subtract from 14, get the pH. What is the buffer? What is the buffer capacity? How to calculate pH of a buffer? How to calculate the pH? We just talked about it. The Henderson-Hasselbalch equation. pH equal pKa plus log of concentration of A minus divided by HA. What are the basic principles? Principle of reactions with acids and metal oxide, metal hydroxide. We talked about in details. You must remember those. They will be in the test. All those questions that I'm asking here, they're all in the test. Of course, I'll not ask like this way. You'll ask in a phrase, that example that I gave it to you, and I'll phrase it in a way, those examples that you must know the basic principle, and then you can solve it. What are the applications of acids and bases in our health? I think I just gave you some. And one of the applications that we talked about, the pregnancy test for the pH and pH. What is the indicator? I didn't write it there. You must write down what is the indicator and what is the use for it. Use for it for many different purposes. We use it. One such use in our health profession is the pregnancy test. And some other tests are also there too. And as you probably know, when people go to the some sort of disease, as epilepsy or some sort of disease, that always the doctor asks, have a test for the pH of the solution, concentration of carbon dioxide, concentration of carbonic acid, bicarbonate. That will determine whether that disease caused due to the pH change or something else. So those are all very good applications out there. Any questions? Do you have any questions for this assignment? You must do it. If you need help, you can come to the office hour, and I can help you as much as I can. But I want you to read those basic principles, the topics, examples, and get prepared, and such that you can solve those questions. If you have a real trouble, just ask me. Okay? Shall I move on? Yes. All right. Next is, so we have done part 1 and part 2. What we have done in part 1, we have done the ionic compounds, the metals, non-metals. We talked about so many things, electronic configurations, ionic compounds, their applications. Then we talked about another type of sort of ionic compounds, acids and bases, and we have talked about in details, and that's with their applications in our health mostly. Next part is a part 3. Now we'll do the molecular or covalent compounds, and that's basically sharing pair of electrons. Everybody ready for this? All right. Let's go to and what do you need to know to make a molecular or covalent compounds? We'll make many, as many as you can. Okay. So what do you need to know is as follows. You know the number of electrons at the outer shell of nonmetals and metalloids. Remember, the molecular compounds are generated from nonmetals and metalloids. The way it goes, nonmetal plus nonmetal. Let me see it here. So nonmetal, the way it goes is like this: nonmetals plus nonmetal. Their general principle, equal molecular compound, equal covalent compound or molecular compound. The same thing, covalent compounds. All right. So that's basically the general principle, covalent compounds. All right. So nonmetals plus nonmetals make it the covalent compounds. That's one such principle. Another one, so it's number 1, and number 2 is nonmetals. All right, nonmetals plus metalloids. Metalloids. Let's say metalloids, right? Ml stands for metalloids. It's okay. Nonmetals Nm. S is just many of them. Metalloids Ml. That also equals to molecular covalent compounds or molecular compounds. The basic principle of making molecular compounds: nonmetals plus nonmetals covalent compound or molecular compound. Nonmetals plus metalloids, Ml, metalloids, makes the covalent compound. And how do they do that? By sharing a pair of electrons. How many electrons they will share? That depends upon the number of electrons in the outer shell. All right, and that's in the periodic table. We already know that how to do that. And you can derive the Lewis dot structure. We mentioned briefly, but we'll talk about more details. And why do they share the pair of electrons? Because they want to make a bond, right? In order to make a bond, 2 electrons cannot make a bond. Can they? Answer is no. So if you have a H, for example, electrons, you have H and other electrons, they cannot stay together. They have to spin paired. A tiny magnet, North Pole, South Pole, two tiny magnets, North Pole, South Pole, South Pole, North Pole. Now they'll make a.
Professor Data,
Yes?
it's 11:51.
It is? Oh, all right. We'll continue Friday. Thank you for letting me know. I should have a watch here, huh? All right, all right.
Thank
okay.
you.
You're welcome. If anyone has any question, I'm still here.